So we just did the qualitative description of the LC oscillations and saw how the magnetic energy and electric energy oscillates back and forth. And here we will use mathematics to describe it. Okay. So the total energy is the summation between the magnetic energy and the electric energy. And we learned that the magnetic energy in the inductor is Li squared divided by 2. And the electric energy in the capacitor is Q squared divided by C. Okay, and then we will take the time derivative to see how it changes with time. So it is the time derivative of the magnetic energy plus electric energy. And then remember this inductance L and capacitance C are constants. So therefore only the current I and charge Q are changing with time. So the first time you get Li multiplied by di dt, which is the time derivative of the current. And for the second term, you get Q divided by C multiplied by the time derivative of the charge. Okay, I hope you understand why we get this when you take the time derivative. If you do not understand it, please ask me in the classroom. I will try to explain it, but I hope you understand it this much. Okay. Anyway, here we have the current and charge, and then we want to actually combine them into a single variable. So what was the relation between the current and the charge? We learned that the current was originally defined as the time derivative of the charge, right? So therefore, in fact, actually this term here is in fact the same as this guy. Okay. And then how about this guy, this di dt? So if you take the time derivative of the current, okay, let me write it this way, di dt, this is actually equal to the another time derivative of the dq dt, right? So therefore, it's just like taking the second derivative of the charge, or which means that you are taking the derivative or differentiation of the charge twice. Okay, so you can now write it this way. Okay, and then again this current here, and then this guy is the same, so you actually take them out of the bracket. So this is the current, and all the remaining terms go into the bracket, and then this is 0. Okay, why 0? Because the total energy is conserved, so it does not change with time. Okay, and then since here you have two terms multiplied and you get 0, this means that either of the two must be 0. So therefore, and actually in this case you do not want the current to be 0, because if the current is 0, it means nothing is going on. So therefore the term inside the bracket must be 0. Then you can rewrite it this way. Okay. So this is the differential equation representing how charge changes as a function of time. And then take a look at this. You take the second derivative of the charge, and then you get minus multiplied by some current, and that's the charge. So which function becomes minus of itself when you differentiate twice? It is of course cosine or sine, right? Okay. So therefore, now we will, in this case, use a cosine function. Well, you can use either of the two, but here we will use cosine function, and then we will express charge using this cosine, and then this is a general expression of the charge. So total charge Q, the large Q, is the maximum amplitude of the charge, and then here this omega is the angular frequency of the charge oscillation, and then this phi will be the phase constant. This is a general form. Okay, and then since we have written the charge, now we can immediately get the current by simply taking the first derivative. Okay, so then now cosine function becomes minus sine, right? So you have the minus sign, you have a sine function, and then when you take the derivative, this omega will come out. So this is why you have this omega. Okay. And then the reason why we have this is we actually want to put this back into this differential equation, and then try to find what this omega will be. Okay, and so this is what we are doing. Okay, so this this differential equation includes the second derivative, and then you take another derivative of the current. So then you have omega square. Okay, because another omega comes out, and here minus, and then the sine function again goes back to cosine. Okay, so originally you started from cosine, and then here you have minus cosine because you took the second derivative. Okay, and then how about the second term? Second term is simply q divided by c, so it actually is the same q here, and then simply divide by c. Okay, and then the total amount will simply become 0. Okay, and then take a look at this. Here you have cosine, again another cosine, and here q, also q. So therefore you can use the bracket and to take them out, and then finally it's 0, which actually means minus L omega square plus 1 over c is actually 0. So therefore, by summarizing this, you find out that omega square is equal to 1 divided by LC, or omega is 1 divided by square root of LC. Okay. Now we will call this omega 0 because L is a constant and C is a constant. So therefore 1 divided by square root of LC is also a constant. So we use some kind of constant to represent it. So we will actually call it omega 0 or omega naught. Okay. And then in fact the reason why we have this is we want to express how the energy oscillates as a function of time, right? So therefore let's do that. So this electric energy, which is of course q square divided by 2c, was now put this q over here into here, and then this is what you get. Okay, so this large q, we do not yet know what this large q is, but this is simply the maximum amount of charge in the circuit. So okay, whatever maximum amount you have, what is important is that now total energy will oscillate with the cosine square. Okay, so maximum of cosine square will be 1, so therefore the maximum of the electric energy will be q square divided by 2c, and minimum of the cosine square will be 0, so therefore minimum of the electric energy will be 0. Okay, then how about magnetic energy? Magnetic energy is of course half of Li square, so try to put this guy into this equation for the I, then you actually have the half of L omega 0 square multiplied by q square, and then sine square. Okay, but then try to see this. If you use this, you actually figure out that this quantity is actually equal to q square divided by 2c. So therefore, this q square divided by 2c over here is the same as this guy. So these two energies oscillate like cosine square and sine square. So if you add them two, it just becomes 1. So therefore, they oscillate at the same frequency, and then their maximum value are the same, and then the minimum value are the same. But the important thing is that when the electric energy is maximum, magnetic energy will be minimum, and when the electric energy is minimum, the magnetic energy will be maximum. And this is how we can draw the graph, how these two energies are changing as a function of time. Okay. So we just have seen how the electric energy and magnetic energy oscillate back and forth in a circuit including an inductor and a capacitor. Okay, and this oscillation of energy between two different types of energy is exactly the same as what we have learned in the spring semester from the block spring oscillation. Okay, so here we have the mass M connected to the spring of K, and in this case the total energy was, of course, the kinetic energy plus the elastic energy or elastic potential energy, which was simply the half of mv square plus half of kx square, right? Do you remember it? Okay, in this case, the total energy was again conserved, so therefore the time derivative energy will be again 0. And then, of course, if you try to write down the time derivative, it's written this way. And what is important is that this velocity and this position was related like the velocity was, of course, the time derivative of the position. Okay, right? And this is actually exactly the same as such that the current is simply the time derivative of the current that we have seen in this case. So therefore, this phenomena is exactly the same and the solution look the same. So therefore, the position here can be written using a cosine function, which means that this guy will move back and forth like cosine function here. So this phenomena is exactly the same. So this is the same graph that we have seen in the previous slide. This graph also represents the case of how kinetic energy and potential energy oscillates back and forth. Okay, so therefore, as a summary, let's try to make a table which directly compares between this mass spring system and the LC oscillations. Okay, so in the block spring or mass spring system, the total energy was the potential energy plus the kinetic energy, and potential energy of the spring was, of course, half of spring constant multiplied by the position square or displacement square. Okay, and the kinetic energy was, of course, half of mass multiplied by the velocity square. And in the LC oscillation, the electrical energy is half of charge square divided by the capacitance, and the magnetic energy is half of current square multiplied by the inductance. So in all cases, the energy was expressed in the form of half multiplied by some constants multiplied by the quantity square. Okay, and these quantities, in the case of block spring system, this displacement and the velocity was related in such that the velocity is the first time derivative of the displacement. And, similarly, in the case of LC oscillation, this charge and current was related in such a way that the current is defined as the first time derivative of the charge. Okay, and finally, the angular frequency of the oscillation is determined by the constant given here, this Km and then Cl here. See that only this capacitance written in the inverse form, so therefore it will show up. And then, of course, finally, what we find is that the square of the angular frequency in the case of block spring system is, of course, K divided by M, and in the case of LC oscillation, it is 1 divided by LC. So therefore, what it means is that if the mass is very heavy, then it will oscillate slowly, but the spring constant is large, it will oscillate very fast. And in the case of LC oscillations, if the capacitance is very large, oscillation will be very slow, and also inductance is very large, then oscillation will be slow. So there is some similarity and a subtle difference, but essentially mathematically they look exactly the same. So this will actually help you understand what is actually going on in the LC oscillators. And now this time we will add this resistor to the LC circuit. So this is RLC circuit. Okay, so just like this, we have an inductor, capacitor, now a resistor. Okay, so what is going to happen when we have this resistor in the LC circuit? Of course, when the current flows through this resistor, this will generate heat, right? So therefore, the energy will be lost in the form of thermal energy. Okay, so we have to rewrite this differential equation. Okay, so this time derivative of the energy now is no longer 0, but is minus I square R, because I square R is the power generated when the current flows through the resistor, right? Okay, and then the total amount of electromagnetic energy becomes reduced. It decreases. So therefore, that is why you have minus sign here. Okay. So now, if you summarize it, it actually gives you a differential equation which looks like this. I'm sorry. So, well, I do not actually expect you to understand how we get this and then how we solve this. This is a little bit too difficult for us, but still, let's try to learn something from it. Actually, this RLC circuit is again very similar to the mechanical oscillator, including mass, spring constant, and a damper. Okay, if you go back to chapter 14, we had this mass spring damper system where this when this bar is immersed in the liquid, because of the drag force, the mechanical energy will be lost. And this is exactly the same situation as the electric or electromagnetic energy being lost in the resistor. Okay, so in this case, now the solution of this differential equation can be found just like this, in the same way we did in the chapter 14. So and this figure actually comes from chapter 14, and it shows you how this displacement of this mass changes as a function of time, right? So it actually looks like a cosine function, but its amplitude is actually decreasing by this exponential function. So in this system, we had exponential minus bt divided by 2m, and this b was the this damping constant. And now we can actually use exactly the same figure to represent this time dependence of the charge, and simply by replacing this exponential function by exponential minus RT divided by 2L, which means that this resistance is just like a damping constant, and then this inductance is just like mass. Okay, so and we can also see how the total energy is decreasing by putting this charge into the equation for this total energy, and then what you get is this. Okay, so this is just same constant we had before, but now this is multiplied by the exponential minus RT divided by L. Okay, this factor 2 disappeared in the energy because we have the Q square. Okay, so let's try to think about it. So if you have a large R, then it means that this decrease in energy will be very fast. Why? Because if you have large R, then energy loss will be very big, so it decreases very quickly. And if you have large L, decrease will be slow, because large L means the current is changing very slowly. So therefore, in the beginning there will be no current, and then current will be going on very slowly. So which means there will be small energy loss. So that is why when you have a large inductance, energy loss will be very small. And then how about capacitance? In fact, this capacitance does not affect how the energy is changing as a function of time. Okay. And then actually this situation, including resistance, is more like a real situation, because any real circuit will have some resistance. Okay. So therefore, in any circuit, energy gets lost. But then how do we actually keep the machine going when the energy gets lost? This is actually the same situation in the case of this spring mass damper plus motor. If you have a motor, in spite of the energy loss, you can still drive this oscillator, right? And just like that, in this RLC circuit, if you have a device works just like motor, you can still drive this circuit. And such a device, which works like motor in the electric system, is called the alternating current power source. Okay, and this is what we are going to learn in the next pages.